Hello and welcome to this clip on electrophilic substitution of alkyl and acyl groups onto arenes. These are sometimes called Friedel-Crafts reactions because they're a special type of electrophilic substitution. So this clip will assume that you have some of the basics in place already, such as electrophilic substitution mechanism in aromatics. You've covered nitration of benzene rings and their halogenation as well. So in the context of this clip, an alkyl group is any aliphatic carbon-based chain that is attached to another molecule. An example might be this CH3 group attached to a benzene ring, or perhaps an ethyl group like this second one. So they'd be named as methylbenzene or ethylbenzene respectively. So an acyl group is of similar structure but contains a C-double bond O within its own structure. So effectively what it does is adds a ketone or an aldehyde to a benzene ring. So these two would be called phenylethanone and benzaldehyde respectively. So what this clip will do is look at the way that these compounds are made using electrophilic substitution. So in order to do this properly, so it's fully understood, we need to do a quick review of electrophilic substitution and also the use of halogen carriers, because we use halogen carriers to create the electrophiles that are needed, that are highlighted in red on the diagrams on this screen. So in other words, in order to create the species that's in red, so it can actually substitute onto the benzene ring, we need to make an electrophile that carries a positive charge, just like we've looked at before. So the main thing to remember in that it's a substitution reaction is that one atom or group of atoms, so in this case the electrophile A+, replaces another atom or group of atoms, in this case the hydrogen atom bonded to the carbon in the benzene ring. Which leads us to our generic sort of mechanism that we've got at the bottom that can be applied across to several different electrophiles. So what I'd like to try now is I'm going to put a tick by all the places you get marks for, see if you can work out what the marks are actually given for. So have you worked it out yet? You can see that there's 2 marks in the middle and 1 mark either side within the whole mechanism. So the first one is for the correct curly arrow from the ring to the electrophile. The second one is to show the curly arrow correctly coming from the carbon-hydrogen bond to the open part of the partially delocalized pi system, the U shape in this particular case. Your third mark comes from the correct structure of the intermediate, which includes the correct orientation of the partially delocalized pi system, pointing the open end pointing towards where the substitution is taking place. And the final mark comes from the correct products, including H+. So don't forget the H+, which was originally attached to the benzene ring. So it's worth also pausing for a moment just to have a think about what happens to the electrons in the pi system. So we start out with 6 electrons in the delocalized pi system, but 2 are donated to the electrophile. So that leaves 4 electrons delocalized over 5 carbon atoms in the partially delocalized pi system. So I've highlighted the 5 carbons of interest. And I've also highlighted the carbon where there's no delocalization taking place at this point in the mechanism. So let's look at what happens next. So what the curly arrow actually shows is 2 electrons moving back into the partially delocalized pi system. So by the end of the reaction, or the end of the mechanism, there are 6 electrons again and the fully delocalized pi system has been restored. So what we're going to look at now is the creating the electrophile in the first place by a halogen carrier, how the electrophile is applied to the general mechanism we've just looked at, and then finally how we regenerate the catalyst at the end of the mechanism. So to make an electrophile that will halogenate an arene or an aromatic ring, we have to make a halogen ion that is positively charged. You're used to seeing halogen ions as negatively charged, such as Cl-, Br- for example. We need to make Cl+ or Br+. So therefore it will be able to act as a strong enough electrophile to attack the delocalized and stable pi system. So to do this we need a substance that is able to break the bond between 2 halogen atoms in a halogen molecule, which is quite difficult. So these are usually trihalides of aluminium or iron. And the bonds between the metal and the halogen have some covalent character, so they can exhibit electronegativity towards a halogen molecule. So as you can clearly see, what's happened is the halogen-halogen bond has been broken to produce either AlCl4, for example, which has a negative charge, or FeBr4-. It's just worth pointing out what's the halogen carrier in this and what's the electrophile. So once you've made your electrophiles, they're now ready to react with a benzene ring. So to do this, we mix the halogen carrier directly with the aromatic species at room temperature. Not forgetting, of course, the fact that the halogen has to be in there as well, so AlCl3 plus Cl2, for example. So if we apply this to the general mechanism we looked at a few minutes ago, obviously the Br+, for example, behaves as an electrophile because it's positively charged and it's strong enough as an electrophile to attract a pair of electrons out of the delocalized pi system. So if you're asked to write the overall equation, you can actually use structural displayed or skeletal formula, provided you're clear in what you're doing. If they actually ask you for a particular type of formula, then obviously you've got to follow the instructions and there'll be marks available for that. But you can see where you'd put the identity of the halogen carrier. If you were to do an overall equation, you put it above the arrow. The reason is because it's behaving as a catalyst, because it's regenerated. So we'll look now at how it's regenerated, therefore how it behaves as a catalyst. So if we take a look at the mechanism one more time, you can see there's a hydrogen ion produced at the end. So therefore, if you remember the reaction that created the electrophile, we also produce something called FeBr4-. Now the two highlighted species can react together to regenerate FeBr3. It could have happened with AlBr3, for example, as well, or even AlCl3 if we were chlorinating, but we're going to use the bromination as our model at this particular point. But just bear in mind that you can apply this to either an AlBr4-, or if you're chlorinating or iodinating, you change the halogen round, of course. So as you can see, we get the halogen carrier back and also a hydrogen halide, HBr in this case. Now if we get the overall equation that we looked at earlier, it must also show the HBr or the HCl, or the hydrogen halide, as I've mentioned. It's really, really important that you have the correct products, as in two of them. Okay, so I think now it's time to try a quick exam question on this. So when we're applying this across to alkyl and acyl groups, you've got to remember that the same idea applies here as well. You need to create an electrophile using the same mechanism as before. So if you've been looking at my other clips, you'll probably have seen me use this picture a few times before. It's exactly the same idea here. What you've got to think about is, what is A+ going to look like? What is it actually going to be? So here's a little exercise for you. On the bottom I've given you three aromatic species. All of them are substituted. Why don't you pause the clip and try to draw out the displayed version of the structural formulae below before working out what the electrophile is that actually substitutes. So hopefully you came up with those structures. Now what you've got to do is think, what's the electrophile that's going to substitute? So the way to do it is visualize in your mind what's substituting on there and then give it a positive charge, so it's like A+ in the mechanism that we've got on the screen. So because I've highlighted them now, we can add them in. So hopefully you can think about what the electrophile is going to be. So hopefully these are the kind of things you're thinking about in your mind. And what's really important to remember here is the exact location of the positive charge, because that's the carbon that's going to bond to the benzene ring. So although you can write CH3+, I'm actually going to change that a little bit, as you can see. So now let's have a look at what it might look like in mechanism form. So what you're doing is, if we take the R group as an organic species of some kind, to substitute that R group onto a benzene ring, you've got to turn that organic species first into an electrophile. So as we've looked at before, the only reagents that are strong enough to do this are halogen carriers such as AlCl3. But there's a slight problem. The organic species has to be halogenated so that it has a halogen atom for the halogen carrier to remove, otherwise nothing will happen. So here's a little challenge for you. Can you suggest a halogenated species in each case that will create these electrophiles in the presence of AlCl3? So those are the three answers. I'll just quickly draw in the structures so you can see them in displayed form as well. So those are your three structures, and I'll just highlight what would be removed by the halogen carrier. So in each case what would happen is the species would react with the halogen carrier, just like Cl2 would react with the halogen carrier, to leave behind the electrophilic species in black, which would go on to attack the benzene ring. So here's another exercise. Try to complete the equations on the left to show how the electrophile is formed. You'll need to pause the clip to do this, obviously. So there's your correct answers, with the correct species underlined that would react. So now let's put it into action in terms of the mechanism itself. So if we start with the overall equation, we can break up the mechanism into three steps. So what they'll need you to be able to remember and apply is the creation of the electrophile, the electrophilic substitution mechanism itself with the curly arrows, and then finally the regeneration of the catalyst. So I'll take you through the alkylation one first, and then I'll get you to have a think about the acylation one before I show you how that one works. They're very similar to each other, provided you follow the principles we've talked about. So we've got the creation of our electrophile. Now we can draw in the electrophilic substitution. So we've got the benzene ring, and the electrophile, the positively charged electrophile, is nearby. So notice I'm using the one that I've generated in the equation. Now what I'm going to do is I'm going to improve that a little bit by drawing out the structure of the C2H5, so I actually have the exact carbon atom where the curly arrow is going to move to. So hopefully that's now a little bit more clear where exactly the curly arrow points to. So now I've got my intermediate correctly drawn out, and I break the carbon-hydrogen bond. A pair of electrons move into the partially delocalized pi system, regenerating it to a fully delocalized pi system, but now I've got ethyl benzene, and I've also produced H+. So obviously now what can happen is the AlCl4 can react with that H+ to regenerate my catalyst. So it'll look something like that, won't it? Producing your AlCl3 again. So why don't you pause the clip and have a go at acylation. So if you visualize it, it shouldn't be too difficult. It's exactly the same idea. The creation of the electrophile is basically taking the chlorine atom off your species that's above the arrow. So notice how I make sure that my positive charge is above the carbon, which is actually going to bond onto the benzene ring. Thinking ahead a little bit, it's this carbon here which has to have the positive charge. So that's where I've put it. So if I line up my electrophile like that, I can put in my curly arrow. As always, starting at the ring and pointing directly at the positively charged part of the electrophile. Giving me an intermediate species that looks something like that, I now have to break the carbon-hydrogen bond, pointing my curly arrow clearly into the open end of the partially delocalized pi system. And that gives me my substituted phenyl ketone, phenyl ethanone in this case, not forgetting my H+ that has come off. So no surprises what's going to happen here with the regeneration of the catalyst. It's exactly the same as we did before, isn't it? Okay, so I think it's now time to try an exam question or two. I'm going to do a couple actually. I'm going to do an easier one first and then a slightly more applied, harder one after that. So the first thing it asks you to do is to consider compound P, which has a benzene ring with an electrophile attached to it. So what you've got to do is visualize the electrophile. So obviously it would be that part of the molecule. So then it says two substances that react together to form the electrophile, and write an equation to show the formation of this electrophile. So the first substance is CH2CH3ClCl, Depending on what part of your A2 course you're on, you may have done naming of these types of compounds, acyl chlorides. It's called propanoyl chloride. If you're in the summer part of your first year, so just on your end of your exams, and haven't started your A2 year in September yet, you won't have come across perhaps how to name these, so don't worry too much about the propanoyl chloride. Sorry about the helicopter in the background. So, it's worth pointing out that chlorinated or brominated versions are fine here because it's the final substituted product you want to pay attention to, not necessarily the exact halogen carrier used to get there. What I would say though is obviously if you use a chlorinated species you need to have a AlCl3. If you use a brominated species you need to have AlBr3. A little bit of common sense perhaps needs to be applied. So that's the equation that we're looking for. Don't forget the positive charge on your electrophile in the right place. So let's now put the ticks by where you'd pick up the marks. Okay, so let's move down the page a bit and have a look at the next part, which is to outline a mechanism for the reaction of this electrophile with benzene to form P. So let's make some room. So I start by drawing out the structure of my electrophile and placing it nearby to my benzene ring. Notice how I'm positioning the carbon that's positively charged so that I can easily draw out my curly arrow. So drawing the structure of my intermediate, that now gives me another mark. So let's just check our marks so far. So we've got the correct curly arrow in the beginning, then we've got the correct structure of our intermediate. We now need the curly arrow on the intermediate, don't we? And we pick up a mark for doing that as well. But unfortunately here there's only 3 marks on offer, so you need to put the correct products in anyway. It shouldn't be too difficult because if you've studied the electrophilic substitution mechanism by now, it's just a case of applying it across to this idea. So now let's have a little look at a more difficult or applied version. Right then, this one obviously has a reaction scheme as opposed to simply just one particular reaction. When you see this type of question in an A-level paper, they're asking you normally to consider several different parts of the specification. So looking at it closely, you can see that you've got an alkyl group being put onto a benzene ring, and you've also got the conversion of that into a alkene, and you've also got additional polymerization of an alkene. So there's actually quite a lot going on here that we need to be aware of. So there's nothing really to worry about, just the fact that you've got several things from several different parts of the specification going on at once. So what the question will do is ask you to consider each part of those in turn. So the first part asks us to identify 2 other substances needed to carry out the reaction in step 1. And notice it says other substances, because if we look closely we've already got 2 that are there. Reinforced in the question where it says write an equation for the reaction of these 2 substances with ethene to form the reactive intermediate CH3CH2+. So our substances are definitely not benzene or ethene. So let's think about this for a second. So the question we've got to ask ourselves is, how do we convert ethene into CH3CH2+? So for it to be an electrophile, it has to be chlorinated. But we want the CH2CH3 to be made, so we have to think about how we're chlorinating it. Are we dichlorinating it, or are we monochlorinating it? So if you look at the fact that it's CH2CH3, it must mean that hydrogen has been added to one of the 2 carbons. So therefore, instead of it being chlorine, it must be HCl. So this is an applied version of what we've looked at in this clip, isn't it? We didn't look at HCl earlier as something that would react with AlCl3. We looked at HCl as something that would be made at the end. So let's think about what kind of equation you'd get here. So the equation actually needs to be done in 2 stages. The first stage is to add HCl across the carbon-carbon double bond. So that makes our chlorinated alkyl species, our chlorinated ethane molecule, so chloroethane, and then the chloroethane reacts with AlCl3 to make CH2CH3+, which is our species that we want. And that produces AlCl4. So now what we need to do is put in the mechanism. So if we move the page down a bit, so we've got some room to do that. So it says name and outline a mechanism for the reaction of this intermediate with benzene in step 1. Obviously electrophilic substitution. So if we take our benzene, it's fairly straightforward, isn't it? It's almost exactly the same as what we've been looking at earlier on. So we've got our intermediate with the correct curly arrow showing the carbon-hydrogen bond breaking, and not forgetting the formation of our H+. And finally it says an alternative way of making ethyl benzene from benzene uses chloroethane instead of ethene, and asks you to give one reason why the ethene is the preferred reagent. So the consideration is here that you have one less step. If you have chloroethane as your starting material anyway, you don't have to bother making it from ethene like we've done in the answer above. So let's go back and quickly check where the marks will be allocated on our answers. So if we go back up to the top, so we have a mark each for our two substances, and an equation, both parts of it, you get a mark for there. The mechanism gets a mark as well, so now we can move down and have a look at why you get 4 marks in this place here. So, 1 for your curly arrow, 1 for your structure, curly arrow again, and correct products. And down here, a sense that you understand that by reducing one step in the process, you're making it cleaner and more efficient industrially. Okay, let's go on to the last part of this question. So it's asking you for the repeating unit of polyphenylethene. So let's think about what phenylethene is first. Now what we need to do is think about how this might polymerize. Now clearly your repeating unit is not the original monomers I've just drawn, but the actual polymer, but one repeating unit of it. So it would look something like that, wouldn't it? You'd have your single bond in the middle, not the carbon-carbon double bond anymore, and you must show the trailing bonds sticking out either side. If you don't have them, it doesn't give the same message to the examiner, and therefore you don't pick up the mark. So the type of polymerization is obviously addition. Okay, so that brings us to the end of this clip. It's been a little bit longer perhaps than the other ones I've done, but I think it's useful to start having a look at how they might extend it a bit and push you a bit. So this second question was probably a bit more challenging than the first question, so you can now see the range of questioning styles they might ask you. So once again, thanks for your time, thanks for your patience, and hopefully see you soon.